Hello, folks. As I was going through the release notes for the latest trains for NX-OS standalone, for Nexus 9 K switches, obviously, there are some features that seemed quite interesting and exciting. So I wanted to, explore them into more details and learn more about them. And I thought that it could be a good idea to document my testing and exploration in videos so that on one side, I organize my own notes, and on the other side, maybe those videos could be helpful for the community. So I really wish that you will find this video series helpful. So the first thing that I wanted to dig into more details is everything related to micro-segmentation in NX-OS VXLAN L2VPN EVPN fabrics. Now, with that said, if you want to learn more about this topic as well, I would highly recommend that you connect on the Cisco Live on-demand library and you search for GPO, which stands for Group Policy Option. If at the moment you don't know more details about GPO, that's completely normal. You are at the right place. So this will give you access to some very good sessions from Max Ardika and Kritika Krishnamurthy, who are covering this topic as NX-OS standalone without controller and also with controller, which is NDFC. So these sessions are very good, and as you can see, there are not many sessions on this topic because, again, it's quite recent feature. It was introduced into the train 10.4, which has roughly 1 year as of today, and we are in October 2024. So yeah, highly recommend to check out these sessions. And as you know, when you go on a Cisco Live on-demand library session, when you click on it, not only do you have access to the recording of the video presentation, but also you can download all the material into the PDF format. And speaking about material, I want to make a disclaimer. There are some slides that I took the liberty to reuse into my presentation because they are very well done, very well structured, and I don't want to reinvent the wheel. So when slides already exist to elaborate on my purpose, I'm reusing them. Obviously, there are many slides that I created on my own, but I just want to give the proper credits when I'm reusing slides of other persons. So that's it for the context. Now, if we speak about the agenda, this first video will be regarding some generics on micro-segmentation, what this feature is aiming to address, what are the main pillars that it will be leveraging. Then in the next video, we are going to explore what are the different steps and prerequisites in order to enable the feature. Then we will go to a lab environment where we will get our hands dirty and do some testing. With that said, let's go back to our slides. And start with an overview. Now, if you allow me, I will do some reading of a very interesting element that you can find into the release notes. So to find this paragraph, you simply go to the Nexus 9K series NX-OS VXLAN configuration guide for the 10.4 or the 10.5 train. And you will find what I am mentioning in those slides. So I simply did a copy paste of this paragraph because, again, I find that it explains very well the context and the challenges that we were facing before the creation of this feature. So let's go through it. And we will do some drawings in parallel at the same time. So in traditional data center environment, the application workload security is often implemented at the perimeter or the north-south boundary. And I want to highlight this, the north-south boundary, where the users from outside data center fabric enter. This is often implemented using perimeter firewalls, and I want to highlight this as well, and other security inspection devices. However, this approach is not effective against the advanced nature of attack of late. The attack surface spans the entire data center, including the east-west/north-south flows. So what we are referring to here, so I did a very quick drawing that will hopefully help us illustrate this, but I'm sure that you have ideas very clear on this. But, just for the sake of clarity, let's assume that we have this beautiful fabric there, and we have our users coming from the outside to access the workloads that we have attached to the fabric. So usually what we do is that we position a router there to make the connection between the outside world and the fabric, obviously. And we connect what we call a perimeter firewall somewhere, and we ensure through routing that any flow coming from the outside will necessarily cross the firewall before being eventually allowed to go through the fabric in order to access the workloads. Now, obviously, when I speak about firewall, it can be a firewall, a cluster of firewalls, any other security devices, IDS, IPS, whatever. What is important is that we ensure that we are doing the bare minimum, right? The security, so that we don't allow any traffic to come into our fabric and access our workloads, obviously. Now, there are multiple ways that we can connect all this stuff. This is just a high-level view. Obviously, instead of having a router, we could position a firewall there. The firewalls can be spread across multiple positions. Again, this is just a high-level drawing to explain what they are referring to into the release notes. Now, this is what we do at minimum, again, to protect our fabric. So, using micro-segmentation with security groups and security group ACLs, obviously we are going to come a lot on these notions into our videos. Sorry, I'm trying to highlight, but I'm doing some mess there. This feature can provide effective solution to the users of NX-OS standalone platforms. With micro-segmentation, organizations can provide application-specific policies that specify how the application workloads communicate regardless of where those applications reside within the network. And also to illustrate this, I'm coming back to my slide. I'm removing the part for the outside because, again, this we have covered it. It's something that is well mastered. Usually we never do any kind of implementation without having at least the security for the outside part. Now I want to focus on the inside part now. So this firewall, even though I have positioned it at the same place as the previous slide, it is to do some east-west filtering and security enforcement inside my fabric. It can be the same firewall as the previous slide. It can be another one. It doesn't matter. Here, just what I'm saying is that I'm focusing on the filtering and security for flows from the fabric to the fabric. Obviously, there are some solutions that exist as of today independently of micro-segmentation, right, to provide the security. Well, hopefully we have plenty of things that we can do. The first thing that comes to my mind I want to remind ourselves of is the capability to separate the networks into different VRFs. Now, on my drawing, I have illustrated two VRFs, one that you can see with the links in green and one with the links in purple. The VRF notion gives us a big flexibility and help when it comes to implementing security, because the VRF by definition, they don't communicate with each other. We need to do an extra configuration so that we can perform the leaking. So either we configure the leaking inside the fabric, or we do it using an external point of connectivity, which I'm doing here using the firewall. So actually the fabric itself does no leaking at all, meaning VRF green and VRF purple, without the usage of the external firewall, they are completely isolated. They cannot communicate with each other. If I want this device in green to communicate with this device in purple, I need the firewall. So through routing, I will very easily be able to configure that and attract the traffic. Sorry, it's green first and then purple. So this is really easily configurable through natural routing. Now, when we can rely on routing, things are always easier. So long story short, when we are able to separate our workloads into different VRFs, it's very easy to implement security. But when we consider traffic inside the same VRF, like for example, this host 1 there that communicates with this host 2 on the second leaf, how can we ensure that the traffic cross a firewall, for example, or again, any security device? Now, if they are into different networks, despite being in the same VRF, but two different subnets, then if we don't do anything else, we cannot really easily make them go through a firewall. What we can, by relying on the classic routing based on destination, what we can do is implement what we call PBR. So PBR is something that enhance the routing, I would say, by checking the source of the traffic. So we are not routing just based on the destination, but we are considering where does the traffic comes from a layer 3 perspective. With using PBR, we could catch and match the traffic from H1 to H2 in order to redirect it first through a security device before being able to route it to H2. Now, to implement this match and catch, we would need something like ACLs, right? So ACLs, they have been existing since a very long time in networking. They work well. The thing is that it's difficult to maintain them. When we configure one ACL one day, it's perfectly okay. When we need to configure plenty of ACLs and we need to rely on them for the purpose of security, it becomes quite cumbersome from an operational perspective and the daily life of the network engineers. But at least the solution exists. Now it becomes even more challenging if we consider that not only we are in the same VRF, but also we are into the same network. Because now it's not, we are not relying on routing to make the connectivity between two different hosts, we are relying on switching. Now, how can we implement security between two hosts that are in the same subnet? So we would need to rely again on ACL, maybe MAC ACL, maybe private VLANs. So again, things exist, but we are always coming back to the notion of how easily it is to configure and how easily it is to maintain. I know I'm being quite talkative before entering into the main topic, which is micro-segmentation, but I wanted to refresh our minds on where we come from, what are the possibilities that exist as of today, how did we do till now without the use of micro-segmentation, and how micro-segmentation can help us. So long story short, we can rely on VRFs, we can rely on PBR, we can rely on ACLs, but we want to have a solution that is easily implementable, I don't know if the word exists, and easily maintainable from the daily life perspective. So that was it for the context. Now let's come back to our slides and dig into more details for the pillars of the micro-segmentations. So I would like to start by presenting some main key terminology points when it comes to the implementation of micro-segmentation in the context of NX-OS. The first word that we will be using a lot is ESG, which stands for Endpoint Security Group, and allows us basically to put multiple hosts on multiple destinations into the same group, so that after we are able to enforce things on those groups. So first things first, we need to create those groups and put what we want inside those groups, right? So the ESG definition is a logical entity that contains a collection of physical or virtual network endpoints, which are classified based on attributes/selectors listed below. So we have IPv4 or IPv6 addresses or subnets, VLANs, and VM attributes. Now I want to spend some time on these three elements. So first, for the VM attributes, I have not seen them so far, so maybe they will be introduced into next releases. What I have been able to see and test was the first 2 points, so the subnets and addresses, and the VLANs. And when it comes to the subnet and addresses, there is an important element to mention. It is that we can catch either fabric local or external. Fabric local, it means hosts that are connected to the fabric, and that we basically learn through, either the MAC addresses through the L2 frames or the IP address through HMM, or the external subnets that we can learn through routing, whatever the type of routing, whether it is static or dynamic, through a connectivity with an external device. So we can put all kinds of subnets inside security groups. It doesn't matter if the devices are directly connected to the fabric as workloads/servers/users, or if they come from external world through a routed communication, And endpoints classified under an ESG are assigned a fabric-wide unique tag. The range is from 16 to 65,535. Actually, the range that's spread from 0 to 15, it is a reserved range. Some of the tags that belong to the 0 till 15 range, we are going to see them into the exploration when we go to the lab environment, because they will be basically assigned automatically to specific kind of traffic and specific kind of devices. But we will explore this into more details. The key takeaway here is really that when we create our groups, we will be able to assign a tag to them, and that tag we can configure it from 16 to 65,535. ESG is a pure security construct which has certain match criteria for creating segmentation and uses contract/policy to define the security posture. Now, again, this is very important, right? Contract/policy. It is what we will be enforcing between these different security groups. So once we have created them and once we have put inside of them the relevant devices and networks, we will be able to enforce security policies or contracts between them. Now, small disclaimer, in networking, usually we do like having multiple terminology and namings for the same thing. But basically, when we will be speaking about SG, ACL, or contract or policy, all this refer basically to the way that these different groups will be able to communicate or not communicate between them. So, and depending on the documentation, you will find one or the other, but basically you got the idea. So if I want to make a small drawing regarding this, I would say, for example, I have my fabric here with leaf 1, with leaf 2, and a spine here. I'm thinking that I should have taken another slide, but never mind. So I have server 1 and server 2. I'm saying that I'm creating the security group clients. And inside the security group, I will put my server 1. I will be matching on the server 1's IP address to put it into that security group. And the tag that I will be assigning to clients is 100. Then I create a security group named servers. And inside these servers, I will match the IP address of server 2. I should have named host 1 and server 2, but never mind. You got it, all right? So here I will be putting server 2 based on its IP address, and the security group servers, I will assign it the tag 200. Now with this, I am then able to configure some contracts to say how the security group clients and servers are able to communicate. In other words, how the tag 100 and 200 are able to communicate. So that's the generic ID. And very small addition to the terminology, it's that obviously depending on the direction of the flow, sometimes 100 and 200, if I come back to my example, sometimes 100 will be the source, so 100 would be the source group tag, and 200 will be the destination. So 100 is named SGT and 200 is named DGT. For the opposite flow, opposite direction, it's 200 that becomes the SGT and 100 becomes the DGT. I know it's obvious, but you know, you will find those terms into the documentation. So I just wanted to stress them out so that we clear any confusion. Key takeaway, what we have now is we have understood that thanks to micro-segmentation, we are able to use different criteria in order to put our workloads and external networks as well into some security groups. And to match those workloads and subnets, we are able to use different things. We are able to use either the IP addresses or the VLANs or even ranges of VLANs. And I guess that VM attributes will, if they are not already here, honestly, I didn't see them yet, but they will be soon there, I guess. So the global idea is that we have flexible criteria to match our devices and put them into groups. So that's it. Now I think we can move to the next topic. So now that we have our security groups, what do we do with them, right? What microsegmentation allows us to do with them? Now, there are two main cases. The first one is the most obvious, and it's the one that we have been speaking a lot about into introduction. It comes to everything related to security. Because with this microsegmentation, we are able to create security zones. So VXLAN GPO allows to define policies for enforcing security policies, SG-ACLs, between security groups or SGs. Now you can say, okay, in the beginning I was speaking about ACLs, I was saying that it's not very easy to maintain, etc., etc. And here we are speaking about, again, about ACLs. But I was stressing multiple times in the beginning that the thing is, it's not ACLs that are bad. It's the way we implement classic ACLs with match 10.00/24 to 20.00/24 when we need to track each subnet individually in each ACL, and for each ACL, for each new need that we will have, we will need to think about every subnet, etc. This is cumbersome. It's not the fact that we are defining an ACL, it's the way that it puts burden on us that is difficult. So with SG-ACLs, things are simpler because we are not relying on subnets each time. We do not need to rethink, okay, what are the subnets that I need to allow for this specific use case? And when I have another specific use case, I will need to rethink again about the subnets and reinvent the wheel, etc. Here we are putting things into groups. And once we have the groups, things become simpler because we are no longer speaking about subnets, we are speaking about security groups. Now, coming back to the slide, the next paragraph mentions what I was saying. So SG-ACLs are a simpler, more flexible, and more scalable policy enforcement mechanism compared to traditional ACLs. And it provides better control over the flow of network traffic, both east-west and north-south. Now, what we are referring to here is that, again, since we can match everything, we can use them basically for any kind of traffic, either for the internal traffic between workloads that are connected to the fabric, or between those workloads and devices that come from the outside and that we can reach through a border leaf, an external router, an external firewall, whatever. So this is the first use case, the creation of security zones. And actually there is a second use case, which is also quite sexy. It is the service chaining. So VXLAN GPO can be used to insert network services into a packet flow based on specific policy criteria. Service chaining steers flows through the appropriate network services functions, such as firewalls, load balancers, or intrusion detection systems. Now, what we are saying here, it's quite intuitive, is that instead of having the security group 1 being just allowed to speak to security group 2, we want first that this traffic get redirected to some devices like an LB, an IDS, an IPS, whatever, before being able to communicate to security group 2. So this is the use case of service chaining, and what we will be able to configure with micro-segmentation. Now that we have illustrated the main use cases, I would like to come back to some terminology elements with additional vocabulary. So one of them, which is very important, is the enforcement point. Basically, if we speak about the capability, especially for the use case of allowing of or denying traffic, which is the security zones creations, etc., the position in the network, I mean by that the leaf in the network that will be able to enforce the policy, is what we call the enforcement point. So this enforcement point, basically the global ID is that it can be anywhere. So it can be either on the leaf that is connected to the source or on the leaf that is connected to the destination. Both of them have the capability to call the contract or enforce the contract in order to apply the proper decision. But what is important here, and what we will be spending quite some time on for when it comes to the control plane perspective, etc., is that we want to be efficient. So let's say that we have leaf 1 here and we have leaf 2 here. We have our friend server 1 on leaf 1 and our buddy server 2 on leaf 2. Obviously, there is a spine in the middle, hopefully. And we want that server 1 is not allowed to communicate to server 2. So we will have the policy contract configured on leaf 1 and on leaf 2. But what we want to do, obviously, I should look for a synonym for obviously. At the moment, there is not any that comes to my mind. I apologize for the repetition. So if this flow needs to be dropped, what we want to do is drop it as close to the source as possible. We would rather spare the bandwidth and the transport when the flow needs to be dropped, because obviously we can, saying again obviously, we can route it to leaf 2 and drop it there, but we'd rather drop it as soon as possible. So for that case, for that purpose, we are wanting to seek for efficiency, and we will be looking into the next slides for how we are able to implement this. For now, let's retain that, but from a high-level perspective, both leaf 1 or leaf 2, so both the source leaf and the destination leaf, can be an enforcement point. When it is the leaf 1, in our use case, it is an ingress enforcement. When it is leaf 2, it is an egress enforcement. Another very important element is the capability to transport the tag. So here it is a very short summary that I'm mentioning as just some bullet points, but really this is what I would say represent the heartbeats of the whole solution, because we are introducing the notion of tags. So it means that we need the control plane to be able to propagate those tags across the fabric. Obviously, our control plane, it is our friend, beloved friend, BGP L2VPN EVPN. So far, it had no notion of tag transportation, right? So it means that we need to enhance it somehow so that it is able to transport that tag. So this is from a control plane perspective, overlay control plane perspective. From the overlay data plane perspective, we need as well to carry that tag so that if we need to go to the destination to enforce the policy, then the tag is already present into the encapsulation. Same thing as with BGP. So far in VXLAN, we had no field or no notion of transporting any tags. So it means that we need to enhance VXLAN to be able to transport that tag. How this is done, and I'm sure that you see me coming, we will be calling some RFC, some theory to implement this, but for now we are just referring to the fact that it exists. So control plane BGP will distribute the tags, and the data plane VXLAN will carry the source SGT in the overlay VXLAN GPO header. So we already see GPO pointing his nose here. So the group policy option, but we'll be checking it into a next section. And the last key terminology elements revolve around the configuration that we are doing for our VRF. So we will see in the next 2-3 slides that there are basically multiple options for our VRF to configure how we want the VRF to behave. The first thing is regarding the enforced or unenforced mode. So do we want to enforce the policies that we are configuring or not for the moment? And the second thing is, if we are enforcing the security groups by default, as long as we didn't create any policy, do we want to allow the traffic by default or to deny the traffic by default? So this is two very important things that we will be checking right now. So let me go to the next slide to check the first mode of the VRF, which is VRF unenforced. Hello back. Sorry, I had to stop the video because my computer was keeping crashing, or more exactly, it's actually the software that I use for the record, which is OBS, who was a bit overloaded. I don't know why, honestly, because there are not many stuff that are running on my computer right now. Maybe it's the encoding of the ping that I was wearing, so I decided to change it for another cloth that I know works fine in video. I mean, I'm really not sure of the RCA of the issue. Anyway, apologize for this. So let's go back to the topic, which is more interesting, that's the color that I'm wearing. So we were speaking about the VRF unenforced. So let's check out what this means. Actually, this is the default VRF mode, meaning when we configure a VRF context, the default mode is unenforced. What it means is that we can define security groups and associated rules to classify endpoints and prefixes in specific SGs. We can even configure our SG ACLs contracts, but the thing is they are not enforced in the VRF. In other words, what it means is that we can go ahead on our leaves and configure the different groups that we want. For example, we will configure the SG clients. We are configuring the SG servers. We are assigning the tag 100 to the first SG, the tag 200 to the second one. We are even matching the specific hosts with, for example, the IP addresses to put them into the proper security groups. So, for example, we are putting our host 1 into the security group clients. We are putting our server 1 into our security group servers. We are even creating the policies/contracts to say how we want our clients and servers to communicate. For example, we are positioning a contract that says that clients can only speak SSH towards servers. So security group tag 100 can initiate only SSH traffic in direction to security group tag 200. All this, we can configure it. The thing is, just it will not be enforced. So the host will be positioned into their security groups. It's just that the contracts will be completely ignored, not even checked. What it means as a consequence is that with the unenforced mode, it's not possible to verify if contracts applied between SGs are hit or not. So just step back a little bit and understand exactly what all this means. It means that the unenforced mode gives us the flexibility to be able to go ahead with our configurations, position the security groups, create our contracts. It's just that nothing will be checked. So this is what it means. As long as we are in unenforced mode, we can play around with the command lines, check out how it works. I mean, not how it works, but how it is configured, what is the syntax, etc. It's just that from a VR perspective, from a routing, switching, forwarding perspective, it's like if we didn't enable anything. It's like a classic working of our VRF and our NX-OS that we are used to. So this is it for the unenforced mode. So now let's check out what we have from the enforced mode perspective. Actually, for enforced mode, we have two possibilities. Either we have a default permit or we have a default deny. Let's check out first the default permit. What it means here is that with the default permit, we are able to configure our security groups. So again, let's take the same example, the security group clients, the security group servers, host 1 in clients, server 1 in servers, 100 for the first tag, 200 for the second tag. So we can create our security groups. Now let's assume that we have just created the security groups and we have not created any contract between them, no SG-ACLs, nothing. We have just defined the security groups. When we are in enforced with a default permit, the way it is configured is like in this paragraph. So we go into the VRF context for our VRF. We say that we are doing a security enforce with a default permit. I will come back to this tag a bit later. So the default permit, again, what it means is that we have our different security groups. They are configured. We are specifying the criteria to match the end hosts and the subnets to populate those security groups. It's just that as long as we didn't define any specific contracts, there is a default permit. So all the security groups can implicitly speak with each other with absolutely no limitations. So again, what it means here is that with the enforced default permit, we are creating our security groups. And as long as we did not define a specific contract for what we should do with those security groups, they can communicate freely through classic routing and switching. It means that, as a consequence, if we want a specific type of traffic to be denied, then we need to configure specific SG-ACLs. So by default, it is open bar between all the SGs. If you want to deny some specific traffic or apply some specific things on it, we need to configure those SG-ACLs. Now, I'm sure that you guessed it. What is the behavior for the default deny? It's the same ID with the opposite philosophy. So for the configuration, same kind of logic, we go into the VRF context, we do security enforce, and we apply a default deny. It means that we can configure our SGs, same again with the criteria to position the host and subnets inside the SGs, as long as we did not configure specific policies and contracts. By default, the SGs cannot communicate with each other. So it means that with a default deny, the only traffic that is allowed is a traffic from a specific security group to hosts from that same specific security group. It is the only type of traffic that is permitted. If we want to permit any other traffic between the SGs, then we need to configure explicit security group ACLs. So this is what we call the zero trust that is enforced. So key takeaway, when we are in enforced mode, we can configure just one line of configuration into our VRF to say what we want to do by default, meaning when we don't have specific contract between SGs. Do we want the traffic to be by default permitted, so we need to configure specific rules to deny it? Or do we want to deny it and configure specific security groups to permit it? So that's it. Now, before moving to the next points, I would like to take just a few minutes to mention an important consideration. So let's say that we have our fabric, our VXLAN L2VPN EVPN fabric that is living happily without any kind of security group being enforced, without any stuff related to micro-segmentation being implemented. And we are thinking about how to move from these stages to a new kind of implementation where we would have our security groups and our policies being configured and applied, right? So how do we do that transition? What is the quote-unquote smoother way to operate? So I would like to say that a possibility would be to leverage this kind of implementation, which is VRF enforced with a default permit mode. Why? Well, because with this kind of implementation, there is a very interesting thing that we mentioned, but is quite helpful when we want to move from a world where we have nothing to a world where we have policy implemented, is that when we define our security groups and our contracts, we can check if the contracts are being hit or not from a statistics perspective. So we can see if we have something being incremented. So what I mean by this is that if we take back our beautiful fabric from the beginning of the presentation, and let's say that we have host 1 here, and we have server 1 here, and we want to be able to configure the proper contracts so that only the supposedly allowed, so only the traffic that is needed is indeed permitted, and the rest of the traffic is being denied. So how can we do this in the smoother way possible? So let's say that we create our security group client and we match the host 1 to put it in there. We create our security group server and we put our server 1. This is security tag 100 and this is security group tag 200. Then we are going to create, for example, one contract to say SSH permitted. Then we are going to create one contract to say HTTPS permitted. Now, everything that will be corresponding to SSH will make the counter for this policy being increased. So we will be able to show it in some show commands. And the same thing goes for the second contract. So we will be able to see some HTTPS being hit. Now, if the application goes through other kind of communications, we will not be disrupting it, because in any case, since we are into enforced permits, if we have not defined the specific contract that is permitting this, it will be permitted by the default, I would say, implicit rule that is being presented there inside the leaves. So we are able to see to be able to see some contracts being matched without disrupting the communications between the hosts. So if we think that there are more ports that need to be open, we can configure additional policies and allow them explicitly and check out if that contracts are being hit or not. Now, obviously, this is not a perfect solution to understand exactly how the applications communicate. At the end of the day, it's out to the application guys to communicate to the network persons what are the flows that need to be open. By the way, usually it's never, I mean, all the flows are rarely listed extensively and precisely, right? Okay, I wanted to make this joke because in most of the cases, they always say that it's the fault of the network, right? So I'm just taking the opportunity of this video to tackle a bit this discussion with the applications person, whatever. This is not the perfect solution to identify what are the flows, right? We need the application persons to tell us what are the flows. We can also launch some captures in the network, some spans, some taps, whatever, in order to have a proper visibility on the flows that should be explicitly permitted or matched or redirected or whatever. But still, this is, I would say, a possibility to check out what are the kind of traffic that effectively flow between our host 1 and server 1. I mean, it's just one possibility, right? So I wanted to mention it because it's still something interesting. And by the way, as far as I have tested, today we can have the visibility only at the granularity of the policy, meaning if the policy calls multiple SGACLs, we will still be able to see the stats only on the policy level. So it means if we want to see at the visibility of the SGACL, sorry, at the granularity of the SGACLs, we would need to specify multiple policies, but maybe this will change into the future. But in any case, you know, I'm not saying that this is the perfect way to see how your flows are going through the network. I'm just mentioning that having enforced permits is interesting because of those elements. And then obviously, when you want to configure proper security, you should be considering at some point in time to move to enforce deny, which is really the thing that implements real security, because unless you have permitted something explicitly, it will be dropped. And the last thing I want to mention before moving to the next slide is regarding where we configure things, and then how we are going to allow for the proper contracts to take effects. Because multiple times you have heard me speaking about configuring those two security groups that I'm mentioning again and again over my examples, but where should we configure them? So actually, we should configure the security groups in all the leaves on which the VRF is implemented. Why? Well, simply because the host can move from one place to another. A very important element that we are going to see into the configuration and that we have already mentioned is that we can match basically anything. We can match something that is connected to the fabric, so end hosts that belong to the fabric, as well as external subnets. When it comes to matching the connected, and this is a very important highlight that I want to make, it means really physically connected to a specific leaf. It means that if I want to be able, in this specific deployment, I mean really this example that I'm showing on the slide, if I want to be able to put host 1 into the security group clients, I need the help of leaf 1. It is just leaf 1 that is seeing host 1 being connected and has the ability to ensure that host 1 is tagged with 100. The same goes for leaf 2. It is just leaf 2 that has the server 1 connected, so it is leaf 2's responsibility to ensure when it learns about server 1 that it puts it into the security group servers and assign it the security group 200. What I mean by this is that despite the groups and their security tag associated will be configured across all the leaves where the VRF is defined, it is just the leaves that have the host being attached at a specific point in time that have the capability to position the tag for that specific endpoint being learned. In other words, if you recall the way of the process on which that the Nexus 9K leverage to learn about the IP addresses, it is the HMM, right? And HMM, it tracks the communication of the attached endpoint, so really physically attached to one specific leaf. It means that leaf 2 does not have the capability to put host 1 into the server group, sorry, the security group client. It is really just leaf 1 that can do it. So the consequence of this is that when host 1 starts communicate, and same for server 1, leaf 1 will assign host 1 with the security tag 100, and leaf 2 will assign the server 1 with the security tag 200. So then come multiple questions, right? How can I ensure that leaf 1 knows about the security tag that is being assigned to server 1? I'm sure that you see me coming because this is a kind of transition towards the next big section. It is the enhancement that is being added to the control plane. Now, obviously, our control plane for the fabric, it is BGP, L2VPN, EVPN. So BGP, L2VPN, EVPN has been enhanced in order to allow for the tag propagation across the fabric. So once leaf 2 has learned about the existence of server 1, in a classic world, in BGP, L2VPN, EVPN, what it would do is enable leaf 2 to generate a route type 2 with the information of server 1 and send that route type 2 to the rest of the fabric. With the extension and the enhancement that was brought integrated to BGP, L2VPN, EVPN, not only it will announce the reachability information, so the NLRI of server 1 with the path attributes, but it will also add the information of the tag. How it will do this, we will check it later. For now, we are just seeing the global view and understand why we need what we are going to speak about. I always like to dig into why do we need what is being implemented. So this is from the control plane perspective. Now, let's imagine that still we have a situation where, for whatever reason, leaf 1 doesn't know yet of the security group of the server 2. How does it do? Now, it will need to, when host 1 sends traffic towards towards server 1, it will arrive on leaf 1. Leaf 1 will create the encapsulated VXLAN packet to send it across the fabric to reach leaf 2. Now, again, let's imagine and let's assume that we have a situation where leaf 1 do not know the security tag that is applied to server 1. It only knows about the security tag that corresponds to host 1. It means that leaf 1 is not able to enforce the security policy. So leaf 1, if you remember some slides ago, we were speaking about the enforcement point. Leaf 1, ideally, we would like to make it as an ingress enforcement point. But again, here we are assuming a scenario where leaf 1 do not know the information of the security group tag of server 2. Obviously, in order to be able to apply a proper policy, it needs to know two things. It needs to know the security group tag of the source. It needs to know the security group tag of the destination. If one information is missing, it's not able to know which policy should be applied, so it doesn't apply anything, and it will rely on the destination to apply it. But the destination, we need to carry inside of the packet the information of the source group tag. Again, I'm sure one more time you see me coming. In classic VXLAN implementation, into the header, we never heard about a place where we position a security group tag, right? This vocabulary is quite new. It's inherent to micro-segmentation. Well, like BGP, which has been enhanced, VXLAN as well has been enhanced in order to be able to carry the security group tag of the source inside the VXLAN header. And this is also something that we will be digging into using the next section. This was just a high-level overview, again, to position the different pieces of the puzzle. So that's it. It means now we are ready to see what are the enhancements that the brilliant community engineers who write the RFCs implemented to allow for the micro-segmentation to work properly. A very last element before moving to that section is some general considerations in bulk. There is no really relation between these different points. It's just some important things, in my humble opinion, that I have noted when I was going through the release notes and the different documentation that I have checked to build this video. So this feature is supported on VXLAN EVPN fabrics. It means that if we take Nexus 9Ks outside of a fabric, then we won't be able to enforce micro-segmentation. It's really something that is related to VXLAN EVPN fabrics. Something that is important as well is that the ESG with IP selectors will be used for segmentation of both routed and bridge traffic. Actually, the most quote-unquote tricky element to consider is bridge traffic. What it means is that when we have a communication between our our host 1 and our server 1, even if both of them are in the same subnet, for example, they are into VLAN 10, in order to match the host 1 with its security group clients, we will still rely on host 1 IP address, not on host 1 MAC address. This is what this sentence means. So for both bridge traffic and routed traffic, the SGT and DGT will be derived from the source IP and the destination IP, not the MAC address. Then some generic things that are permitted by default, by implicit policies without the need of defining them explicitly. The control traffic to and from the SIP is allowed by default, fortunately. And the micro-segmentation is not applicable to multicast and is not applicable to BEM traffic. In other terms, all the things that we are configuring with SGs and the policies is to match unicast traffic. Unicast switched traffic or unicast routed traffic, whatever, but still it is for unicast traffic, not BEM and not multicast. So that's it. We are finally ready to go to the theory and the RFC parts. So let's check it out. First, let's have a look at the data plane elements. I would like to start with a very brief reminder of VXLAN header. Now, as you know, VXLAN is defined into the RFC 7348. It's a very interesting documentation to read because it defines everything that needs to be understood to implement properly a VXLAN in any kind of fabric. The goal here is not to go over the VXLAN details because really everything that comes to the specificities of VXLAN, they are still relevant for what we are doing here, meaning the L2 VNIs, the L3 VNIs, the concepts, even the concepts of VNI itself, everything is the same. The only thing that I want to highlight here is the difference when it comes to the VXLAN header. Now, if you go to your RFC 7348 and you check for VXLAN header, it is actually this section that is very important when it comes to the comparison between the VXLAN classic implementation and what we are doing for micro-segmentation, because it reminds how the VXLAN header should be implemented into the classic implementation. Now, let's check out how this header is encoded. So we have first some bits, which are called the flags. So in the flags, there is only one bit, which is the I bit, that must be set to 1 to mention that we are carrying a valid VXLAN network ID, so a valid VNI. The other of the fields from the flags, which are called the R bits, are actually reserved fields and must be set to 0 on transmission and ignored on receipt. So it is the fields that I have surrounded here in blue. So all these bits are set to 0 on transmit and they must be ignored on received. The only bit that is set actually to 1 is the I bit to say that we are carrying a valid VNI identifier. Then we have some reserved bits here. Sorry, I'm never talented in highlighting stuff. Let me try to do it again. Erase. Good. The pen. So we have reserved bit here and we have reserved bit here. But the logic is basically the same as the R bits into the flag part. So the reserved fields, they must be set to 0 on transmission and ignored on receipt. This is a very important element actually, especially for the backward compatibility that we will be speaking about. So VXLAN implementation RFC mentions really explicitly that all these R bits need to be set at 0. And the last part of the header, obviously, it is the VNI that we know. So it is the field that allows for the encoding of the virtual network identifier. So again, this is not our interest at the moment. What we will be focusing on is the R bits, which is very funny because usually in most of the presentations, the field that we really don't care about are these R bits that are reserved and are set to 0 because those usually the documentation mentioned that these are reserved for a future implementation, so we are not considering them now. What is funny for this specific recording is that we are in the use case of a specific implementation where we are leveraging some of those bits in order to allow for the feature that we are considering, which is micro-seg. So let's check out how this is implemented. So the enhancement that was brought to VXLAN is named VXLAN Group Policy Option or VXLAN GPO, which is the acronym that I was mentioning in the very beginning of the presentation. So this is where the GPO comes from. There is actually a draft for an RFC that has been written. I would highly recommend that you check it, not only because it's always important to see the theory of the RFC, but also because it's actually quite short, so it's very easy to read. So it defines what is the enhancement that was brought to VXLAN in order to allow for carrying the proper fields that are relevant to enable microsegmentation. I have tried to take the most important points of this draft and I did a copy paste of them into my slides. So let's check them out together. The first element is that it introduced a terminology point. So I have not mentioned it yet already, but basically it's the same thing that we were referring to. when we were speaking about our host that ends up in security groups, is just say that actually the interfaces that are connecting to those hosts or to those networks, we are calling them tenant system interfaces, and we are assigning them to tenant system interface groups. Again, it's the same idea with a different terminology, but the same thing. We are taking hosts, workloads, VMs, servers, subnets, etc., and we are positioning into groups that the RFC is calling tenant system interface groups. Now here I have put in perspective the VXLAN header, which is the VXLAN of the original RFC 7348, and the VXLAN header for the VXLAN GPU draft. And by the way, the GPU also names this header as VXLAN-GBP extension. It's very difficult to say. GBP is for group-based policy. So VXLAN GPU equals to VXLAN with GBP extension. It's all the same. We are speaking about the capacity to transport information of groups, right? Is all what it is saying. So let's see what are actually the fields, or more exactly the bits, that were reserved into the classic VXLAN implementation header that have been leveraged inside the VXLAN-GBP extension. So I have again surrounded these parts of the flags, and as we can see, the R here is being used as a G bit. We see as well that there is a bit here that is being leveraged as a D. And finally, we have the A here that was as well reserved here that we are using there. And finally, some bits at the end to encode the group policy ID that were as well reserved. So as you can see, there are multiple bits that were reserved into the original RFC that now are being used to allow for the implementation of VXLAN GPU. So let's check them out into more details, and I will be spending quite some time on this slide because it is very important. The first bit is actually the most important, the G bits. So let's check out what it means. So for the G bit, the bit 0 of the initial word is defined as the G, or group-based policy extension bit. When we have G equals 1, it indicates that the source TSI group membership, it means the SGT, so the group tag of the source of the flow, is being carried within the group policy ID field. So the group policy ID field being this field there. And it's defined in the end of the slide. So it is a 16-bit identifier that indicates the source TSI group membership that is encapsulated by VXLAN. So if I take again my same example to which I have been referring to 1000 times, if I have my host 1 here with the group 100, which is then the source group tag, it means that the VXLAN with GBP extension would carry the 100 here. So 100 would be encoded there, and the G would be set to 1. On the opposite, if I have a G set to 0, it indicates that the group policy ID is not being carried. So it must be absolutely set to 0 as specified into this RFC. Why is this bit so important? It is because basically, at least as by my understanding, it shows whether we are into the world of classic VXLAN 7348 RFC, or if we are in the world of VXLAN GPU draft / RFC. If G equals 1, it means that we understand VXLAN GPU, and in that case, we need to transport into the frame the group policy ID of the source of our flow. If G equals 0, it means that we need to ignore all the rest of the bits that are reserved. And this is not only important to say if we are implementing one or the other, but it is also important when it comes to a backward compatibility point of view. But I will mention this into more details into the next slide, because it all relies on that to be able to provide communication between environments that support GPU and environments that do not support GPU. Because at the end of the day, we are bringing enhancements and we do not want to we do not want to hit a wall where this enhancement would create a barrier or a communication that would be impossible between the two kind of implementations. We still want to be able to communicate between fabrics that implement GPU and fabrics that do not implement GPU. And it all relies on the Gbit and the philosophy of that bit. But let's check out in the next slide. For the moment, let's continue with the rest of the bits. So there is then this D bit, which is defined as the do not learn bit. When set, this bit indicates that the egress VTAP must not learn the source address of the encapsulated frame. So what we are saying here is that we want to say to the leaf2, do not learn from the VXLAN packet the source of, so the source VTAP on which the source of the flow is attached. To be fully transparent, I have not yet understood the relevance of this field into the implementation of VXLAN, BGP, L2 VPN, EVPN, because in fabrics that use VXLAN with the control plane, which is L2 VPN, EVPN, we never learn in the data plane anyway. We learn the host reachability through the control plane. So having the D bit set to don't learn, it is just an addition to what we are already implementing, meaning that we are not learning anyway from the data plane. So I don't really see what this brings. Maybe it is for VXLAN fluid and learn. Again, honestly, to be transparent, I still didn't understand the full interest of this, but I will be checking it and either commenting the video or making an addition into a next video. In any case, and what is most important for me, is that the draft mentions that we must not learn, which is actually what we want. We must not learn. We are learning from BGP. We are not learning from VXLAN. So it's coherent. Now let's check the next important bit, which is the A bit. It is the policy applied bit. It allows us to say whether the policy has been applied on the source leaf or not. So if we come back to the previous example, where we are considering this fabric, if leaf 1, that is here, was able to apply the policy for a communication between host 1 and server 1, then it would set the A bit to 1 to say, okay, I know that this flow should be permitted. So when the encapsulated VXLAN frame reaches the leaf 2 will check the A bit. It will see it as being set to 1. So it understands that it doesn't need to make any enforcement. The policy enforcement has already been made by the leaf 1. Leaf 1 has already done all the job. So if we put things together and we consider a flow between host 1 and server 2 and server 1 that should be permitted by the fabric, what leaf 1 does is that it tries to retrieve all the information that it needs, meaning the source group tag, the destination group tag. From there, it will do a lookup into its configuration. It will find out a policy that allows the communication from 100 to 200. Then it will create the VXLAN encapsulated frame with all the fields as usual, the source header being the VTAP of leaf 1, the destination being the loopback 1 of VTAP 2. I mean, all this stuff, but it will also add the bits that we have mentioned, meaning the G bit equals 1. In the group policy ID, it will position the security group tag of the host 1, which is 100. And it will say, okay, buddy, I have already applied the policy. So please, when you receive the traffic, simply route it or switch it as you would need to do. But just be aware that the policy is already applied, so you don't need to do anything. So this is pretty much it for the important fields of the VXLAN GBP extension header. Now, if we move back to the backward compatibility on which I teased multiple times, the the RFC for GPU has this paragraph that I have copied past on the screen because it is very interesting. What it says is that the original RFC, being 7348, it requires the result fields to be set to 0 on transmit and ignored on receive. It is what we reminded some slides ago when we were refreshing this RFC. This ensures that the G bit will never be set by VXLAN VTAPs. Again, here what we are referring to is VXLAN VTAPs implementing 7348 and not aware about GPU. So those VTAPs, they will never set the G bit. And therefore, packets received from these VTAPs can be assigned to a default group policy ID. And this is very, very important. It also ensures that VXLAN VTAPs receiving packets with the G bit set will ignore the group policy ID. So this small paragraph is giving us hints about a kind of traffic between a VTAP supporting GPU and the VTAP that doesn't support GPU for back and forth traffic. So let's check it out quickly in a small drawing. Let's say that this one supports GPU and this one supports only the original 7348. So if this VTAP sends encapsulated traffic, positioning the G bit equals 1 and consequently all the other stuff that we have checked together. This leaf, it doesn't support GPU. So what does it do? Sorry. It does not drop the traffic because we are implementing backward compatibility. It will see that the G equals 1, but it doesn't care because what the RFC is telling him is, hey buddy, if you see G equal 1, just do not care about these bits. Just ignore them. Just care about the rest of the fields that you know, which is the VNI, which is the rest of the header, etc., and do the proper forwarding, bridging, or switching, whatever you need to do, just do it, and ignore anything related to GPU. You don't need to care about it. This is what we call backward compatibility. On the opposite, if we have the return flow that is initiated from this leaf towards the leaf that supports GPU, here obviously the G would be set to 0. Then what this leaf should do, it should have the capability to assign the hosts that are being encapsulated into the those VXLAN frames, VXLAN packets, sorry, to a specific group policy ID. So this is what is said here. The packets received from these VTAPs can be assigned to a default group policy ID. So anything that we are receiving from VTAPs that do not support GPU, when we receive that, those hosts, we are going to assign them a kind of default group policy ID for the sake of policy enforcement, which allows us to apply some policy enforcement on leaf supporting GPU, even if the traffic comes from leaf that do not support GPU. With that, we have allowed back and forth communication between the two words. So this is what allows us to have a mix of devices supporting the VXLAN group-based policy extension and devices that do not support it. Now, I would like to add a latest point for this is what is the frontier between the hosts that support GPU and the hosts that do not support GPU? What I mean by this is, at which granularity are we allowed to have this? Is it in the same fabric or between different fabrics or something else? From what I read so far into the release notes, when it comes to the Cisco's implementation, it is said that we are able to provide this between different sites of a multi-site implementation. Multi-site in the understanding of having really the real multi-site as designed by Cisco, with the different sites interconnected with border gateways. So this is the pure definition of the multi-site, the ones where we have different sites and the communication is permitted by devices that implement the border gateway function, whether it is specific devices allowed for that or collapsed spine border gateways, whatever, but we need to have those border gateways. So provided that we are in a scenario where we have a VXLAN EVPN multi-site, then we can have a mix of the two worlds, so one site or multiple sites that supports GPU communicating with one or multiple sites that do not support GPU. But inside the same site, we need to be consistent. Either we support or we don't support, either we implement or we don't implement GPU. And I think it makes sense because it would be quite difficult to implement a situation of a situation where we have mixed things inside the same site, and it would be quite cumbersome, and also maybe from an operational perspective, it doesn't make that much sense. So at least this is what I read so far, that we can have a mix at the level of a multi-site. So now that we have checked the enhancements that were brought to the VXLAN, let's check out the enhancements that were brought to the control plane to allow for the stack propagation. So if we check again our drawing, where we are here is that at this stage, let's assume that we have leaf 2 that learns server 1 and it assigned the tag 200 to that server 1. What we need now is that leaf 2 communicate this tag to the rest of the fabric through the route types 2. And also what I want to mention is this thing not only applies to the servers, but when we are doing, let's say we have a routing protocol between this leaf 2 and an external router, router 1. Let's say that we are doing, I don't know, OSPF. We are learning some networks and we are redistributing them into BGP for the rest of the fabric. So here we are learning the external subnets and we are assigning a tag to those subnets. We want as well that tag to be redistributed, not redistributed, but attached to the redistributed networks that we are sending across the fabric. So long story short and key takeaway, we want to be able to spread the tag that we are assigning locally so that the rest of the fabric is also aware of the tag corresponding to that specific end host or specific network. So for that, we are checking the enhancements to BGP L2VPN EVPN. And here we have again an RFC that I also highly recommend to check. For the same reasons as the previous one for VXLAN, it's interesting to read, and the same as for VXLAN GPO, it is quite short, so it doesn't take a lot of time to review. The name of the draft is Group Policy ID BGP Extended Community, and by the way, in the title you see already where the magic lies. It is an extended community. So the way that we are carrying the tag is through an extended community. So what the RFC says, it reminds that for group-based policy, a group policy ID, also known as a group policy tag, is used to represent a logical group that shares the same policy and access privilege. And this specification, meaning this draft, defines a new BGP extended community that can be used to propagate the group policy ID through a BGP route advertisement into the control plane. So what we are adding to the BGP updates is an additional extended community, which is actually a transitive opaque extended community in which we are encoding the group policy ID. So it's quite straightforward, right? It's straightforward because multi-protocol BGP was built to allow this flexibility. It was built to allow for adding new attributes or new extended community. Extended communities is one kind of attribute, but it was created with this flexibility in mind. If we have a new use case or if we have a new requirement, any kind of new needing, we can easily transport it into the update by defining an additional field that carries this specific attribute. Obviously, we need to write the RFC standards to explain the definition of this attribute, but adding it, it's quite straightforward thanks to the MPBGP RFC that I highly recommend to review from time to time just to refresh the knowledge, right? Well, so this brings us to the combination of control plane and data plane. And by the way, what I will mention into the next slides is another draft that was written, but actually what it does is more or less taking the two drafts that we mentioned, the one for VXLAN GPO and the one for BGP with a group-based policy extension, and putting them into the same draft. So let's check this out. So what I was referring to is actually this very latest draft, which is named EVPN Group Policy. Now, what this draft does is not really introducing something new in comparison to the other ones, but is actually kind of combining the two, because we have seen the first one, which is VXLAN Group Policy Option, and defines the extensions that were brought to VXLAN to allow for this micro-segmentation implementation. And the second one that is related to the enhancements to the control plane, which was named Group Policy ID BGP Extended Community. So it takes the two and it kind of makes a summary of these two to explain what are the requirements when you want to implement proper microsegmentation. It also introduces a summary of how backward compatibility should be allowed and implemented in order, again, to allow for the communication between sites that support GPO and sites that do not support GPO. But basically, it is the first two that are being summarized together. Again, I would highly recommend having a look at all these RFCs because even though I have tried to summarize the main takeaway of these different drafts, nothing replaces checking the documentation on our own. So with that said, we have reached the end of this video. I hope it was useful. In the next one, we will be reviewing what are the prerequisites and the different steps when you want to configure GPO on a working VXLAN L2 VPN EVPN fabric. So thanks a lot for watching, and I will see you in the next one. Please take care.